Hello, everyone. This is the Disaster Response Drone Team, group number 2 from Rutgers, sponsored by L3 Harris. Our capstone advisor is Dr. Phil Southard. Our L3 Harris mentors are Howard Cohen and Manoj Visalbaran. Our team members are Angie Flores, myself, Taylor Hansen, Juan Beltran, and Ashish Serene.
The motivation for our project is, as natural and man-made disasters are becoming more frequent, our disaster response drone will reduce the risk taken by emergency responders when surveying a disaster-struck area. Another consideration behind our implementation is to provide a cost-effective solution as compared to similar products on the market, which cost thousands of dollars more than our product. Next. The objectives that we have are deploy a drone to survey disaster-struck areas, develop a computer vision algorithm which analyzes video from the drone to identify survivors in these areas, integrate these two ideas into a deployable product which can aid emergency responders in their search and rescue efforts, and make it cost-effective so that all communities have the ability to use this product.
Our scope of work implements a drone to retrieve the live video from those disaster areas, including information such as GPS and timestamps. We will use that video and this data to identify survivors efficiently and to minimize rescue intervention to maximize their safety. In order to do this, we will implement a basic drone operating procedure. This is to ensure the seamless coordination between emergency responders, the drone, and our computer vision algorithm. In order to do this, we need to satisfy initial conditions and review precautions. Then, determine and allocate regions within that area to be searched. This means separating them and then launching the drone to survey those separated regions. The live stream video that we collect from that, we will analyze using a computer. Also recorded will be coordinates of the survivors, times of identification, and other information such as significant risks in the surrounding areas. Then we'll coordinate with emergency responders to retrieve those survivors. Meanwhile, we'll monitor those emergency responders as the rescue attempt is made and continually reassess the situation for changing conditions.
Our capstone design can be divided into 3 modules: physical module, an AFI drone; programming module, video processing using Python; a lumpy library module to let the other 2 modules communicate with each other. Next. Here we have got specifications for an AFI drone, flight time, wind resistance, vertical camera, and flight controller, whose specifications are mentioned at the bottom of the slide. Next.
As my teammate actually explained, Olympi is the library that provides a programming framework to control the drone in the simulator, but it should be noted that it could be used to control the physical drone in the future. Here are the 4 steps we took to set up the Olympic library, and also ran the Parrot spins, which is the simulation tool. Next. Here are the 2 important classes from the library that we use, which are video streaming and also GPS data. Next.
For the computer vision algorithm for human detection, we use deep learning and OpenCV. The use of deep learning for object detection was done through OpenCV DNA module and a mobile net pre-trained model, which was trained in the CAFE framework using the COCO dataset. With this, we could get predictions from neural net and process them to determine the accuracy and location of the person. Another method that we consider was the HAAR cascade, which is a method that It works like a classifier and takes as input of positive and negative images. But the accuracy that we got here wasn't as much as that we got with a neural network. Next. The design approach and the features for our projects are the following. Remote operation for a computer or a controller, which is the aerial view comparable to helicopters. Also, we have GPS coordinates and date and time stamps displayed. Also, several ready-to-go features that are reliable for a drone and help us to have a predetermined flight path at the beginning. The computer vision identifies survivors through dumb video. Finally, we have a reduced cost compared to similar products on the market. The cost of our drone, the NAFI, is $700, and to get additional batteries is $100 per battery, and this will allow us to have more flight time. This is relatively much cheaper than the current products on the market, which can range from $3,000 to $5,000.
The challenges that we have encountered in our research were determining scale of work to be done within allotted time, increasing efficiency of computer vision algorithm, integrating software in hardware, and working remotely due to social distancing guidelines. Next. Here is the algorithm to increase accuracy. First, we remove the less probable detections. Second, output the most probable detection and remove those which have rather high overlap with the most probable detection outputted. Next. Here is the Python implementation of the same algorithm as shown in the last slide. Disclaimer, we have not researched it in too detail as of yet, but here's the 6-step process. Next.
Here are the constraints we encounter regarding the drone operation. The first one is extreme weather, which includes strong winds and heavy rain. The flight time and the range could also affect the performance. The accuracy can be improved, but there was not enough data set available for humans recognition. The fourth constraint was the location of the person. It also adds complexity to detect the person, whether it's under debris or not. And if we want to add better quality parts, it will be costly for the project. Next. Here are the 4 positive impacts of our project. First one, saving more people from disaster was our top priority. Costs could be reduced significantly from commercial products. The third one, we wanted to decrease the number of emergency responders risking their lives, and also provide them opportunity to plan their rescue events more efficiently. Next.
Our final result of the implementation between the drone and the computer vision algorithm resulted in a proof of concept in which we show the computer vision being implemented on scenarios similar to those that would be encountered in disaster zones. And the Olympi Library simulation in which we showed the drone controlled from a computer taking off and identifying people from afar. Next, we'll show a live analysis of video using the computer vision algorithm. Finally, we would like to thank Professor Phil Southard, our L3 Harris mentors Howard and Manoj for their support and guidance. Also, Dr. Hannah Godrich and the ECE department. They played an important role in the completion of this work. Thank you. Also, thank you for your time, and go Rutgers!